Hi, so I finally got a bit more time to play with these LCDs and the little cheap camera modules featured in a video a while ago. Still got a few ideas of what these are going to be used for, but at the moment I'm just in the process of actually looking at all the various camera modules I can find and just to see which one's most flexible. I mean, most of them will do simple things like you can change zoom factors by fiddling around with formats, and you can do a simple freeze frame by just not updating the display. And I suspect these are going to find their way into some sort of interesting installation in the not too distant future. And as part of the process, I've been sort of basically buying all the cheap camera modules I could find, just to have a play around and see which ones are most suitable. And there's quite a variety. There's quite a few. I've even found some that are about $1 for a sort of XVGA type resolution module of this sort of style. And that sort of really got me thinking, well, what else can you do with a lot of cameras which don't necessarily involve direct display? And the one thing that came to mind was the classic sort of matrix style video effect, where you have a large array of cameras sort of all pointing at a subject from different points of view, that you take either a simultaneous shot or a sequence shot to get some interesting video effects. And I thought, well, might it be viable to use a whole bunch of these things to get that sort of effect? And if you could, how cheaply could you do it? So it's not really something I plan to do. The point of this video is really just to put some ideas out there and maybe, perhaps even inspire someone to give it a go. Yeah, it's the sort of thing I find an interesting technical challenge, but the final thing I'm not that particularly interested in. It's the sort of thing if I built it, I'd end up sort of building it, and then it wouldn't actually get used very much. A bit like my high-speed camera project. But sort of as a engineer, I sort of take this sort of my mind's always sort of ticking away in problem-solving mode in the background. So I've sort of actually given quite a lot of thought to how you might do this. Obviously, you need the camera, but what's the minimum you need to attach to that to actually be able to make a whole bunch of these take basically simultaneous photos, and what can you strip out of the process to get it down as cheap as possible. Now obviously doing something super cheap, it's not going to be sort of super high cinema quality. Obviously one compromise of course is the actual lenses that these things use, but one thing you could do if you're doing some sort of device like this is you maybe sort of start off with supporting something like this, but all you need to do is add some holes on the PCB to take something like this, which is a holder for standard M12 CCD camera lenses, CCTV camera lenses, and that will then give you a choice of some sort of quite a wide variety of lenses. Obviously, the other issue of this is, of course, that single lens has got a fixed field of view. You might be able to maybe select a couple of fields of view by zooming on the camera at the expense of resolution, but as soon as you add an M12 type mount, you've then got quite a variety of lenses from sort of fairly sort of telephoto to fisheye, and you can even get zoom lenses which are not particularly expensive in this format. So the nice thing about that is it's a sort of scalable solution. So you've got the absolute cheapest possible solution, but you've got a potential upgrade path to improved lenses. And another thing you could do is, if you're sort of wanting to go a little bit more serious on this, sort of production-wise, is instead of the ready-made modules, you could actually just use the actual camera chips. Although these are BGA, they're not a particularly fine pitch. I mean, it would be viable probably to route these on a 2-layer board, so that's well within the capability of sort of most surface mount assembly and even home assembly. It's not particularly onerous. But the nice attractive things about this is it's a camera and a lens all packaged up in a nice, easy to use package. So, I mean, what do you need? Obviously you need the camera module, you also need some memory, and you need something to actually control it all. I mean, the sort of general concept I was sort of thinking about was, you have a little PCB that's got your camera module and some memory and something to control it, and then you just have a whole string of these that are just connected up in a chain. At the end of the chain you've got some interface which ends up as USB. And these, obviously, you want to absolutely minimise the cost on these. So ideally, you'd want one cable that's got power and data. In terms of what you're actually passing around, obviously, I'm thinking, to be really useful, you'd be looking at something on the order of maybe 50 to 100 cameras on a nice system. So if you're doing a simultaneous shot, then clearly you'd have to store the image locally and then download it later at sort of probably one by one. So one compromise is that the actual download speed could actually end up being quite slow, purely because of the number of cameras. Even if you can get quite a good data rate across this, you're still downloading potentially an image from 100 cameras. But I think that's a reasonable compromise if you're trying to do stuff on the cheap. And in terms of data rates, I think the answer to what the data rate is basically whatever you can do cheaply on whatever this interconnect was. So I think there's probably a couple of options in terms of the control. There are quite a few microcontrollers now with camera interfaces on them. However, most of the ones I've looked at are fairly expensive. We're looking in the like £5-6 sort of region, because they also come with things like LCD interfaces, Ethernet, large flash memories, various other peripherals, because they're designed to be part of a system, like a digital camera type system. But also, okay, they've got interfaces, Ethernet, you might be able to use Ethernet, but certainly you don't really want to have like a separate Ethernet port for each of these. You might be able to do interesting things using the Ethernet hardware, or possibly even USB hardware, as the basis of maybe a sort of chain type communications protocol, where you can just get data, certainly at least one-way data, fairly quickly for the download. And in terms of what information you want to be passing through here, in terms of sort of going this way from the, let's say your PC or whatever that's controlling it, you want to be sending obviously frame trigger information, configuration data. So that's actually quite a low speed data. Your most onerous timing requirement on this is getting accurate synchronization between the cameras. So as long as you're down in the sort of tens of microseconds, and that'll be fine. And so all the data you want to be sending forward is things like when to take the image, maybe what delays you want to add, maybe some camera configuration. Obviously most of your data is going to be coming back this way, which is the actual image data. So something using the maybe a USB or an Ethernet peripheral might be viable, but I think that's probably going to end up moderately expensive. Also, quite a lot of those chips tend to be coming BGAs and other fairly unfriendly packages. So another issue with microcontrollers like that is you're going to need a moderate amount of memory, at least probably something of the order of a minimum of say 4 to 8 megabits to hold a decent sized image, ideally more, because again, from the point of view of keeping it cheap, you don't really want to be getting into JPEG. Okay, you might be able to have a processor that locally does JPEG compression and then sends the image, but I think you'd be paying quite a lot for that processing power. So I think the way to go would be to basically deal with relatively raw data, have an FPGA control it all, and have a local memory, probably SD-RAM, because that's just about the cheapest memory. So you'd have enough SD-RAM to hold 1 or maybe 2 or 3 raw uncompressed frames that you then send back in a fairly raw format, that then your PC could do all the encoding, compression, all the other sort of stuff that you want to do. You could also maybe send back low-res preview images, so you could actually select a particular camera and get it to send back a semi-real-time preview image for camera alignment and focusing. Just on the subject of sort of raw versus compressed formats, there are some cameras, for example this is an OV2640, which does have some onboard compression. Now I've not read the data thoroughly enough to know whether it actually does full JPEG or just provides some hardware assistance for the JPEG process. Bear in mind, these are all quite old, some of these like 10-year-old models, so it may well be that you can now get camera modules that basically give you a JPEG out. That may give you some other options in terms of sending back much less data, because if you've got compression in the camera, but there may also be issues. For example, they might not be they might have a fairly limited compression rate. So if, for example, you want to grab like a bunch of frames really quickly, you may find that raw image may still give you the best bang for your buck on that. Because I'd imagine trying to do JPEG in video frame rates on like a small cheap camera, my guess is it probably won't do it, but I may be wrong. Maybe there are some cameras that will stream JPEG at sensible speeds, and that might change some of the parameters of this whole thing in terms of how much memory you need. But I think probably the answer would be you still use your minimum size SD-RAM, but it means you can store more images there. There might also be some scope for doing some really simple compression in the FPGA, for example some run length compression, that sort of thing, just to reduce the overall amount of data you're sending back. In terms of image formats, generally these things will output either RGB or YUV. The YUV tends to be sort of the first stage of JPEG compression, so generally you're going to end up wanting some sort of compressed format by the time you're actually outputting anything. So you'd probably be wanting to run this in YUV format anyway, rather than RGB, purely just to get the best resolution and image quality out of it. Right, so before diving in on just technical design and so on, let's just have a look at just a quick reality check on costing. So this is purely looking at the cost from Farnell DigiKey, easily obtainable prices. So this is sort of pretty much a high estimate. So camera module chip, couple of dollars. FPGA, I think you could do it with something of the order of the $4 mark. These are 100 off prices. SPI flash to hold your FPGA configuration, those are just ridiculously cheap, especially from people like Spansion. You can get 4 megabit SPI flash chip for under 20 cents, about 100 off from DigiKey. SD-RAM, basically I just went to it, DigiKey, just searched for SD-RAM and just did a search by price. Cheapest comes out to about 85 cents for 16 megabits, but for another 15 cents you can get 64 megabits, so that'll be enough to hold a few images. So it might be nice to be able to capture a few images as a short sequence or something. So for example, if you wanted, let's say you had a circular array of cameras, you might want to take sort of a sequence of images going one way, then maybe go back again the other way, to almost create like a sort of virtual motion control type effect. So for another 15 cents I think it'll probably be worth going up to 64 megabits, and obviously you could expand that based on how much budget you want to spend on it. But I'm really looking at get this thing cheap as possible. Power supply, you'd need a DC to DC converter on there. I'll explain that in a second. Some sort of oscillator. One possibility though is you might actually be able to figure out some sort of data format where you actually encode some clock information. For example, if you use something like a Manchester code for this, you might actually be able to get the clocking information off the data bus to avoid the need for a local oscillator. But let's assume we need an oscillator just to keep things simple before we start really trying to squish it down. Connectors, that's a fairly arbitrary figure, and again I'll talk about connectors in a minute. Passive components, PCB assembly. So I reckon in 100 offs, without really trying very hard, you'd be looking at somewhere of the region of $15 per camera cost. So 100 camera setup, $1,500. Is that worth doing? I'm sure there's probably people that would say yes, maybe. But the nice thing about it is it's modular. You could just buy as many cameras as you want, string them together, club together with a few mates to get a few cameras each, so you can do different setups. And so that's before you even start looking at Chinese pricing. I'm sure you could almost certainly get that below the $10 figure if you get a few quantities. Maybe if you start thinking about Kickstarter type projects. I think $10 a camera is probably a realistic figure for, obviously this will just be a PCB, bare PCB, nothing, no casing or anything. Right, another quick reality check is just to look at the power issues. Again, these are some just very, very rough estimate figures, which are probably at least within the right order of magnitude. So camera, SD-RAM is probably the biggest one actually. When you've got the SD-RAM running, that's probably taking a fair amount of power, but the figures from the data sheets are based on running it at its full speed of like 100 megahertz. Now in practice you'd be probably down at about a tenth of that in terms of the data rate you'd be dealing with these cameras, so that's probably quite a significant overestimate. But those figures come to around 350 milliwatts. So let's say you're running at 3.3 volts, which is what your circuitry probably is going to be doing. You've got this string of cameras, and obviously 100 milliamps at 3.3 volts, that's going to get a bit ridiculous. 100 cameras is going to be 10 amps, which, okay, you could potentially do it with lots of cable feeds, but you need heavy cable. But the other issue is at 3.3 volts, you're not going to be able to tolerate much voltage drop on that. So you're not only pulling 10 amps, but you're pulling 10 amps and being not really sensitive to voltage drop. So I think it will be pretty essential to have a DC to DC converter on there, so that your actual power supply that you send down the cabling is 12, probably maybe 24 volt. At that point your figures get a bit more sensible. So at 24 volts you'd be looking at like 100 cameras, 1.5 amps, which depending on the cabling used is I think viable. You could obviously feed it from maybe both ends, maybe have 2 or 3 taps in the middle. So if you could feed like 25 cameras off a single power feed, I think that would be more than sensible. So I think you need a DC to DC converter on there. One issue though, of course, is the SD-RAM only actually draws much power while you're actually doing that, taking that picture. So I think maybe with the addition of a big capacitor on there, you might actually be able to reduce this power issue significantly, so your standby power is relatively low. I think you'd still need a DC-DC converter, but you could maybe get away running down as low as 12 volts. But I think 24 volts is a reasonable compromise between sensible DC-DC converters and efficiency. So I think you'd probably be looking at putting a DC-DC on there to do that. So I think from both the cost and the power point of views, it looks like it might be viable. It might be a viable thing to do. So let's start having a look at some detail. So I've actually sort of spent quite a long time just in background thinking about this and about how I go about solving it. So I don't have any intention of actually building this, but I just want to sort of put some ideas out there and just see if there's any interesting feedback or anyone actually wants to go with it and actually try to do it. So I mean, this is what I think you'd end up looking at. FPGA, camera module, maybe you'd stick at least an output to trigger a flash, a LED there, so if you want to do some flash effects, to synchronise flashes and so on, I think that would be worth doing. You have your SD RAM, say 16 or maybe 64 megabits is probably a nice sort of size purely. Again, we're looking at doing this as cheaply as possible. You'd probably want an oscillator on there, SPI flash to load your FPGA configuration. Probably the best candidates I've seen for FPGAs, again on a very quick look, are either the Lattice ICE40 series. Now the ICE40 has onboard non-volatile memory, but it's one-time programmable, so I think you'd probably want to have an SPI flash just so you could reload the FPGA configuration if you wanted to, and it's just so cheap, it's just really a no-brainer. 20 cents to be able to upload it, I think that's just a no-brainer. There may be scope for doing some clever things with this actually, because in principle you could load that SPI flash over your data interface. Generally the way the FPGA works, it stores its internal configuration in RAM, and then when it powers up it loads it from SPI flash. Now you can reprogram, once it's loaded then it's not using this flash, and you can actually gain control over it and program it. There's a small risk of bricking the system if you program a bad image into that flash and then power it down, you'll brick the system. But some FPGAs have a way of partitioning this so that you can actually have multiple images. So what you can have is almost like a bootloader on a microcontroller. You have like a safe image that it will always load at startup, and then you can send a command to tell it to load a new image, which is the one that you've downloaded. So I think the scope, that's going to be very dependent on which FPGA you choose, because the features vary quite a lot from device to device. But I mean, another option, these SPI flash chips are very cheap, so you could maybe even just have 2 of these for another sort of 20 cents or so. The other thing is what I'm not sure, I've not looked in enough detail, for example on the ICE40, whether you can actually have like a safe boot image on the onboard memory and then tell that to boot from an external memory. You'd have to look in detail as to whether that was doable. Another possibility is the Lattice Mac X02, which has onboard flash, which again is in system programmable, so that might save you some memory here. So I've not looked in detail about actually which FPGA would be the most suitable, but I think most of the lowest end, even like a Xilinx 3S50 would probably do the job. Might be a little bit expensive, they seem to have gone up in price recently. But so I think the figure of $3 to $4 for an FPGA I think would be entirely doable. Now obviously one important thing is what can you do with this the communications. Obviously we're looking at a string of devices, so we have a connector, which is basically you've got an in and an out. I'll talk about what sort of cabling and connectors that might be a bit later. One nice thing you get with FPGAs is LVDS. This is basically allows high-speed signalling over a differential interface with basically onboard drivers. So once you decide you're going to use an FPGA, almost for free you get this nice high-speed interface. And I think over moderate cable length that will be capable of certainly tens of megabits, if not more. You'd have to sort of look at what actually encoding scheme you used. It could be a Manchester code, it could be even something as simple as a UART type protocol. I've actually done something vaguely similar on a project a while ago, sort of using LVDS on a string of devices to send quite large amounts of data, and it worked quite nicely. One thing you would need to look at though is protection, because obviously these are going straight into the FPGA, and particularly if you've got 24 volts on this cable, and if your connectors were such that they didn't guarantee, for example, that the ground always mated first, you might have some risk of getting the 24 volts on these pins, which would obviously be rather bad for the FPGA. So you might want to look at protection, which might actually start getting quite complicated. You can get, you could use some sort of Xena type device. You can get devices designed for protecting HDMI pins, which that would at least give you ESD protection. But if you're connecting 24 volts, okay, you're clamping device clamps it, but then what prevents that clamping device bursting into flames? You can to some extent maybe use polyfuses or something like that, but also because you're going through the it's not like you've got a common bus, you're actually going through the FPGA. I think probably what would happen is if you did get a short, it would only take out the two devices. I don't think it would destroy the whole chain. So if it's a cheap board, you might be doing so, okay, we'll take that risk, we'll tell people not to power it, plug the cables in while it's powered up. So there might be scope for some cost saving. Again, that's a cost versus robustness design decision. Now, as to how the actual communications work, I think there's basically probably two approaches here. These orange blobs, these are whatever is encoding the data. So it could be a UART, it could be a Manchester decoder or something similar, something which is basically turning this serial stream of data into something that the FPGA can process and encoding the image data back to send it back. Now the reverse data stream, so your PC or controller is over on this side. This side is really simple because basically all you're going to want to do is tell a particular camera, give me your data. So any particular device, all it's going to have to do is either send its image data or just pass the image data from the previous node. So that side of things is actually really simple. Now in the forward direction, again there's a few options here. Generally you're going to be wanting to send information to the whole array of cameras, and then the camera will have some sort of ID to decide whether or not it's that camera that's being talked to. There are some data you might want to send globally. For example, if you're updating the FPGA or if you're sending camera parameters, you may well want to broadcast that. But there will be certain things you want to send to individual cameras, for example timing offset. So for example, when you take an image, you might want to tell each camera exactly when to take that picture, down to the frame or even subframe timing interval. So there's a few ways of doing that. One slight variant on this is basically showing effectively the raw data just being buffered and sent straight on without any sort of processing. This is nice and simple. The problem is that each of these stages is going to give you a little bit of jitter and a little bit delay, which will start adding up cumulatively. So at some point you're going to start getting problems. Now it's really a bit hard to predict what that is without doing detailed measurements. So although this is a simple system, I think it is quite vulnerable to putting a very finite limit on the number of cameras, which okay you could maybe get around by having starting multiple buses and branches and so on. But I think my gut feeling is that might be a bit limiting. So the other option is, instead of having this single encode decode stage, you basically do an encode and decode within each node. So instead of sending the raw data through, you're decoding it into, let's say, an internal 8-bit parallel format or whatever, and you're then re-encoding it, reclocking it. So basically at each stage you're effectively regenerating an accurate clock based on your local oscillator. So your bit timing is effectively getting refreshed at every stage, and the only thing you're adding is a delay, which isn't going to be a problem. In terms of getting your image data back, that's not a problem. In terms of sending the data, okay, yes, you're going to have to, when you're working out your camera synchronization from camera to camera, you're going to need to take that delay into account, but that probably isn't a problem, because you're going to know what it is. You're going to know what this is doing. So let's say you have, I don't know, 10 microsecond delay in each node, you can just add that offset to your camera trigger point. So I think you could deal with that. One of the flip sides, obviously, it does add a bit of complexity. It's going to means more logic in your FPGA, but I think that might be maybe a better approach. And of course there may be some scope for a hybrid approach where you do one thing in one direction, one thing in another. Bear in mind that your data going from your control system out needs much less bandwidth than the return path. So it may be you perhaps could use completely different protocols here. The forward path could be a really simple UART protocol at a few hundred kbits maybe, but obviously you want your return data to be as fast as possible. The other option, of course, is no reason why if you don't mind spending a bit more on cabling, you could have a parallel stream. So you'd have, instead of one data stream back, you could have multiple data streams back. So there's a few options there, but again, I'm really on focus on this is really coming from how cheap can you do this. That's really what I'm trying to get at. So one thing you can do with this scheme, in terms of deciding which camera you want to talk to at any given time, is that if you're actually processing this data, you can do things like have an address byte as part of the packet you send, and then each node maybe increments it or decrements it as it passes through. So let's say, for example, it decrements it, and this device, you send, say, a a value of 6, then each time that goes to the camera, the first camera, it will decrement to 5, 4, 3, 2, 1, 0, and then the cameras will say that when it sees that being 0, it then does whatever you've been told to. So in terms of triggering or whatever, that's the device being addressed, and then it doesn't send it forward. However, I mean, this method isn't actually necessary. There is actually a really sneaky way you can do addressing without this. Going back to this really simple scheme, and again, this is something I've actually implemented. By adding just a very simple control through your forward data channel that simply lets you enable and disable this direct forwarding of data, what you can do is you can send a command that says, everybody turn off your forwarding. So what happens is all the forward channels on all the cameras would switch off, so that what will then happen is that when you send data, the only thing that would hear it would be this first camera. The rest of it, because you've switched off that forwarding, wouldn't hear it. So what you can then say to that camera, you can program that camera with a register that says you are address number whatever, 1 in this case, first one in the chain, and then you can then send a command to that address that says, okay, turn your forwarding on. So what would happen is this camera would then turn its forwarding on. The next camera in the chain would still not have the forwarding, so again you can talk to that next camera individually, give it its address. So what you can do is you can actually go down the chain, assign an address to each camera in one operation, and then go back to your system where you basically effectively broadcast all the data to all the nodes. But now each node now has a unique address, so you can either send broadcast data with let's say you send it as an address 0, or you can send data to any specific camera by just using that address that you previously programmed in that initial setup process. And if you wanted to, you probably wouldn't, but you could potentially program that address into SPI Flash to make it non-volatile. But I think this is a sort of setup where you're going to be plugging stuff in and out, and just literally all you need to do is go through a process when you turn it on to just do that address mapping process, and so that would basically give you all you need. And that's it, that method will work with this or this system. That doesn't really make any difference. All you need is just some way to tell it to stop forwarding, specify local address, and then start forwarding again, and you just go down the chain assigning these addresses. The camera interface is fairly simple. Basically you give it a clock signal, you get the data out, pixel data out, as well as horizontal and vertical sync pulses. Now one thing you can do really easily with this, of course, what you really want is have all your cameras absolutely synchronized. One, the disadvantage, okay, you could set up a load of cheap consumer cameras or Raspberry Pis or whatever to do something like this, but one thing you can't easily do is actually get the cameras exactly in sync, literally the frame starting at exactly the same instant. Which is what you absolutely need if you want to get really good results from this sort of setup. But obviously it also allows you to do things like subframe timing. So for example, you could say you've got 100 cameras and each one has an offset of say 1/100th of a frame. You effectively got a camera that's taking pictures at 100 times the natural frame rate of that camera. And obviously there's issues like its exposure time and rolling shutters and all that sort of stuff. So that may not be too useful. But what you can do really simply is you look at these, you can send your forward data path can have some synchronization method where you just send a regular packet at let's say a frame rate or whatever. So that gives you like a master synchronization over the whole setup, and then it can then easily lock this camera to that simply by this clock is going to be typically typically a few tens of megahertz, and you're getting your sort of syncs out once a line, and then usually there's a big gap and then your frame sync, and you quite often have a separate vertical sync up, which is probably all you need. So what you can simply do is measure the difference between your master sync and the camera's frame sync, and then just skip clock cycles to the camera to just until those are all locked up, so you can actually get all the cameras literally locked to a single within a few pixels really easily. And again, the logic to do that is really simple. You wouldn't need a PLL or anything. It's literally a really simple clock skip and a timer to measure that delay. So my gut feeling is that this FPGA is not going to actually have a great deal of logic in it. It's probably going to need, purely because of the packaging issues with FPGAs, it's probably going to be a 100-pin device, because anything smaller, there's a big black hole in the FPGA market between 100 and like 30 odd pins. One exception is the Lattice Ice40s do have some intermediate pin packages that you might be able to get away with. The camera itself, that's only got probably about sort of 12 odd pins, 14 pins, depending on how many data bits you want to use. You've got obviously 8 pins for your LVDS if you use a single lane. a few other odds and ends. Probably your biggest pin hog is your SD RAM, because you can have 16-bit data purely because SD RAMs come in 16-bit chunks, so you might as well use them all. And from memory, I think you've probably got a similar number of address lines and probably half a dozen control lines. With a 100-pin FPGA, you've got plenty of pins, and I think if you use like QFP sensible packages, I think it would be quite viable to route this on a 2-layer board. If you wanted to make it really small, you could go to BGA, or so you get an FPGA in BGA, you can get the SDRAM in BGA, but I think you need to be up at 4 or 6 layers, but then again it could be like a really small board, so that might not be an issue. But again, I'm focusing on keeping this simple, keeping it practical, because I think this is, it's a very doable thing, and I think it's actually quite practical. So the functionality of this is really going to be not much. It's going to be deciding when to actually start streaming data from the camera, frame of data from the camera into your SD-RAM. It's going to be doing the synchronization. The other thing these cameras have is an I2C interface. They don't usually call it I2C because Philips get a bit nasty about sort of trademarks and stuff, but they call it SCCB or TWI or whatever. But basically there's typically a couple of hundred registers that will set up all the parameters of the camera, and that covers timings, formats, exposures. And although you could potentially set this up from the FPGA, maybe using data from your SPI flash, I think by far the most practical thing would actually literally to stream it from your control system straight through here, straight to the I2C interface. So this is literally just forwarding bytes here. So you do all your setup on the other end, which again means you'd have minimal logic, or literally you'd have a very small command set of commands that come down here, one of which just says throw this byte at the camera, and that's all it would need to do. So you wouldn't, and because that's single direction, you don't need to do the I2C interface would almost be as simple as SPI. Just wiggle the clock, throw the data at it. So you could set all your cameras up, you could set all the exposures, your white balance, your frame rates, all the stuff that you can set up on the cameras quite easily. So this FPGA really it's going to have things like address counters and some refresh control for the SD-RAM, but it really isn't going to be a huge amount of stuff. You don't need a big ass FPGA to do this. Again, I've not looked in detail, but if you're lucky, you can probably arrange things such that one line of data from the camera corresponds to a single page or a section of a page in the SD-RAM, so you don't have to worry about line buffering, or because generally in the SD-RAM you send a row address, then you send a column address, and then you can send a burst of data fairly rapidly within that page, but you then have a delay to access another row. But I think if you arrange your addressing nicely, I think you could probably utilise the fact that you've already got gaps in your camera data at the end of every line, and use that to cover all the setup for the SD-RAM row address. So I think again, this interface, if you spend some time actually looking at the actual address widths and the data coming from the camera, I think you could probably set that up to be a really simple, straightforward, again minimal complication in here. So I think that's that's pretty much all you're going to need in terms of the logic functionality. Power supply, again, you'd certainly want a buck converter to at least get you down to somewhere in the region of 3.3 volts. I've not really looked at availability of SD-RAM in less than 3.3 volts. The cheapest stuff is 3.3, so you might end up having maybe a buck regulator going down to 3.3 volts. Your SD-RAM is probably your biggest power draw potentially, so if the SD-RAM is 3.3 rather than say 1.8 volts, then you'd probably have a buck regulator going down to 3.3, then some LDOs to give you probably 1.8 volt. You probably want to run as much of this as you can as 1.8 volts. The camera's almost certainly going to be 1.8, but also just to reduce power draw. The cameras, most ones I've looked at, need a 2.5 volt analog supply at a fairly minimum amount of current. Some of them actually have an onboard regulator, but I think that's only for the internal 1.8, not for the 2.5. So at the very most, this would be a 3.3 volt buck converter, maybe a couple of LDOs for 1.8 and 2.5. I don't think you need anything else, unless obviously if you started looking at adding flashes, but I think that it would be sensible to do that as maybe a little plug-in subboard or something, because not everyone would want that. And so that's pretty much it for the functionality. So I think we've convinced ourselves this is doable. The cost and the power works out. I think it's plausible at least. Now, in terms of what happens at the end of this bus of cameras, I think that's going to be pretty straightforward. So you start off with your PC or Mac if you want controlling all this stuff, USB interface. So the box that sits at the end would have probably USB 2, maybe something like an FT232H high-speed USB chip. Obviously you've got your cable coming out to the cameras, you'd have power coming in, so you 24 volt, let's say you're using 24 volt supply, you'd have that coming in, you'd have some sort of protection, just protection against cable damage in case you get a short, and then you'd have your LVDS interface. Now that could be probably inside another small FPGA. That's probably going to be the simplest thing, so you can optimise all the data formats and reuse your transmit receive code that you use for the cameras, just interfacing to the high-speed USB. So I think this will be pretty simple and cheap, not really a great deal in it. For scalability, obviously you could use more than one of these and have multiple USB buses, or you could maybe have multiple buses on here, so one of these boxes could serve multiple strings of cameras and still maintaining all the synchronization across all the strings. The other thing you would probably also want is some sort of external trigger input, so you could actually, instead of having the PC tell everything when to actually start an acquisition, maybe you're triggering on some sort of external device, some sort of hardware sensor, motion sensor, a beam brake or sound sensor or whatever, to actually trigger the capture, so you could get you wouldn't be dependent on any time latency in your PC. You'd actually have a hardware trigger path from whatever your sensor is to this FPGA. You could just send the packet that says go to all these things. So but this would literally be USB interface on an FPGA and not really a lot else. Fairly simple. Okay, so we've got a camera thing, but we need to look at some more practical considerations. The first one is how we're actually going to connect these things together. I think there's two sort of standout options here. If you're looking at fairly small arrays over small distances, I quite like flat flex cable. The connectors are nice and small, you can get off-the-shelf cables in a variety of lengths, and it's quite small and lightweight. So if you've got these, if you've got you've got a board or something like this, you're connecting these together. It's not imposing too much stress, so obviously you're not going to want a sort of big, sort of chunky, heavy mounting. I'll sort of have a chat a bit about mountings in a minute, but that might be one option. But of course, for longer distances, for sort of high-speed data, it's pretty much impossible to beat good old Cat5. I think you could get a decent data rate down it. You can, the cables cost next to nothing. The connectors are a little bit big and chunky, so if you're looking, I don't think there'd be much point in going down to like a really small BGA type layout and then to have two massive Cat RJ45s on it. If I were laying out a board, I would probably make provision for both of these options, Cat5 and FFC, and then depending on the scale of the installation you want to set up. Because obviously one nice potential thing about a system like this is that you could actually do stuff on like a really small scale. So for example, you can maybe set up a load around perhaps a bird table or something, so you could actually have an array of like 50 odd cameras in actually quite a small space. So that's where I think FFC will be quite a nice solution compared to Cat5. And over the short distances, the fact that it wasn't a twisted pair I don't think would be a big deal, and I've done fairly high data rates over flat flex cables using LVDS, and it's worked fine over sort of up to like the 50 centimetre sort of distances. There might be some other options. One thing that might be worth looking at is USB 3 cables. Again, from the point of view they're a consumer cable, they've got chunky power cores, they've got nice high-speed data cores. Maybe SATA, I don't know, I've not really looked that closely. I mean, Cat5, just going back to the Cat5 option, if you, for example, have two pairs for your two data, you then got another two pairs spare for power, so you maybe dedicate two pairs for power, two pairs to ground, and it's certainly viable to get about an amp through that before you run into nasty problems over like over like a few tens of meters. So I think Cat5 is probably the standout option. One thing you don't have with Cat5 is any leading ground option, so I think you might have to think about either protection or being quite careful that you don't plug these things in and out while the thing's powered up. The other thing is obviously mounting. You've got these 100 cheap cameras. Now you don't want to buy 100 tripods. Okay, maybe some of the really cheapo ones. So I think you'd have to actually give quite a lot of thought about mounting. In terms of the overall physical configuration, I think the ideal arrangement would be connectors and all your logic on one side and the camera module or camera chip on the other, because that then gives you space for all sorts of different lens mounting options. You haven't got, I think you want to try and avoid having any additional clutter on this side of the PCB. If we're using a module, maybe even have the FFC connector on the other side of the board and have the cable pass through the board, so you've got a completely clean surface to work with, just to give you the maximum possible choices of, say, whether you either want to go for the inbuilt lens option or you want to stick a big sort of zoom lens, or pick up some cheap film SLR lenses or something. So I think that'll be worth doing, but also you need to think quite carefully about how you actually mount this. I think that might be a job for some sort of clever sort of 3D printed or moulded thing, which sort of the PCB goes into. It gives you maybe some tripod screws, it maybe gives you some other screw holes, maybe some means to clip or stick stuff on. One thought I did have on this, if you're sort of producing a nice linear array that you want to then bend around, is actually just get some sort of plastic, sort of flat plastic material that you then have holes drilled in it, so you actually just mount the cameras directly onto that with just sort of simple screw pillars, and then you've got this array of cameras that you can then bend, flex around, that you can then sort of flex around, bend, twist to get your view, so that even if you were to maybe have a tripod to mount each strip, it means you're mounting like 10 or 20 cameras in one go. You just need to support the ends, and the plastic will naturally sort of enforce a nice sort of progressive curve. But I think that's something that would need quite a bit of thought. Okay, you could do just the PCB, but I think you'd have to think about providing as many options like holes and slots and so on, so you can mount it in as many different ways, because obviously different people are going to want to mount this thing in different ways. But I don't think it's a particularly big problem. It's just something that you need to just sit down and give a bit of thought to, providing as many options as possible for the mounting. Right, well, supposing there's actually anyone still watching at this stage after all that technical babbling, I think we've shown that this is technically feasible, and I don't think there's really any doubt that it would work, and I think it could be made to work quite well. The question really is, would anyone be interested in doing it and actually making it happen? So as I said, I'm not really. If someone wants to, I'm quite happy to sort of bounce ideas back and forwards. I think I'll probably start a thread on the EV blog forum in case anyone wants to discuss it. I think it's possibly quite viable as a Kickstarter type thing once someone's actually got it working. So anyone up for the challenge? Go for it.